real quick. Switch share to a whiteboard. Let me quickly sum up all the equations you'll need for this test. You could calculate, delta G from just delta G products minus delta G reactants, but this is only at 25 degrees C. If you want delta G at any other temperature, you need delta G equals delta H minus T times delta S and that will get you delta G standard or non-standard at any temperature. How do you get delta S? Same way you get delta G up here with products minus reactants. How are you going to get delta H? The same way you got delta G, products minus reactants. Look it up in a table. How do you get delta S universe? Delta S universe is just delta G in reverse. It's delta S minus delta H over T times 1,000. And the other big equation is delta G standard equals negative RT ln K. There's maybe one or two other equations for this chapter, and that is that calculate the temperature where delta G is 0 is delta H times 1,000 over delta S. Those are all the equations that come up really in chapter 18. Chapter 19, quickly clear these out. E cell is going to be the E reduction minus the E of the oxidation. So whatever the E reduction of the oxidation is, you subtract those two. We can get that delta G is equal to negative NFE divided by 1,000. And you could use that in reverse. If you have delta G, you can find E. If you have E, you could find delta G. If you have delta G and E, both of these can be related. R, T, NF, ln K. If you have both delta G and delta and E, both of those can find you K. It doesn't really matter which one you use. Doesn't really matter which one you use. Just make sure if you use that abbreviation that replaces RT and F, it switches to a log. Don't make that stupid mistake. And the last one is like Nernst, which is E equals E naught minus RT NF ln Q. How do you find Q? Q is, remember, products over reactants. No solids, no liquids. And finally, there's the mass equals the current times time times molecular weight over NF. Those are the equations for that chapter for 19. There's a lot of equations, yes, but they're all really interrelated. Most of these are interrelated. The only one that's not really related is this first one and this last one. Those are all ones you may be using on this test. So So, okay. Give people enough time to come in. Let's continue where we left off. So one of the big things we use nuclear reactions for, and this is mostly for research purposes, but transmutation. Research and medical and analytical purposes. Oh, come on. Give it a second. Essentially, we create new and heavier elements through collision of high-speed atoms. We have particle accelerators like the relativistic heavy ion collider or the Large Hadron Collider, which we essentially speed up protons and to near the speed of light, and they slam into heavy atoms. And this is how you, among other things, generate, like, say, radioactive cobalt-60. It's how we generate every synthetic element above mass 92. Above 92, none of those really exist. And so how do you make them exist? Well, you slam protons into various other heavy elements and look for fragmentations. And you see, like, oh, what new elements do we have at the end, and see how do they form? And you're trying to measure, do you have any proof that these guys existed even for a second? Some of these only will exist for a second or less before they fragment into A and B. Think, well, if it's fragments into A and B, it must have came from C. And so we have, oh, we made this new element here. But so how will you do math with this? You're going to look at, you can now, instead of just looking at all the decay rates, you can now also look at reactants. And so no matter what, the sum of all atomic numbers and all atomic masses have to add up to zero, had to add up to be equal on the same side. So nitrogen is 7, carbon is 6. So this guy has to be 0, 1. It's a positron. Silicon. Looking at silicon. Silicon is, I think it's 16. I'm going to pull up my periodic table. Silicon is 14. Okay, good to check. 14. 14 plus 2 is 16. 28 plus 4 is 32. So what did I form? I formed sulfur. So if I bombard silicon with alpha particle, I'd form sulfur. Americium can fragment. Americium is 95. Neptunium is 93. So the difference there is 2. And 241 and 237, the difference is 4. So americium undergoes an alpha decay to form neptunium. But we could also look at this as seeing what elements add up to give both sides equal. So okay, clicker 4, so don't take too long, but identify the missing component. So uranium 235, 92, goes to cesium 144, 55, and rubidium 90, 37, and what component? So please note that the atomic numbers on the left sum up to 92. The atomic numbers on the right must also sum up to 92. So whatever this element is, it must add up 55 plus 37 plus blank must give you 92. 235 plus 1 makes it 236. So 144 plus 90 plus whatever must give you 236. Now there's an alpha particle, which is helium atom, 2 neutrons, 2 positrons, or 2 beta particles are the options. Once again, send me an email if your clicker isn't working. Got a few more minutes. It's been too long on this, but okay. I give it to this 2-minute mark. Ready, steady, and stop. You guys are pushing it. Someone is. So you add up 92 plus 0, 92. 55 plus 37, that's 92. 144 plus 90 is 234. So 234 plus 2 would give it 236. So this produces 2 neutrons, or B. Crap. Or B. Okay. Okay, so shame Danny boy isn't here. At least I didn't see him. Gonna miss this, but it'll be in the video. So nuclear reactors, how do they actually work? So most nuclear reactors work on uranium-235. We bombard them with a neutron in one form or another, and it undergoes fragmentation as it fissions off into 2 different elements. And they produce either 2 neutrons if it goes through this fission reaction, or 3 neutrons as it goes through this reaction. The idea here is that for every 1 neutron used, you produce 2 neutrons or more. And these neutrons will then strike more uranium atoms and essentially generate more fissile products and keeping this chain going. Now, there is a certain degree of percentage of fission reactions that do not happen, that the neutrons bounce off harmlessly and get absorbed and do not result in new fissions. And so we have to keep a critical mass of uranium needed to keep this reaction going, so that at least the first neutron, for every 2 or 3 neutrons formed, one of those 2 neutrons or one of those 3 neutrons are absorbed. So we have at least enough to keep it going at a constant rate. And that's why that's what's called a critical mass, just the right amount of uranium in a certain arrangement so that we can keep this going. Now, unfortunately, uranium-235 is only 0.71% abundance of all uranium. So meaning, in order to get uranium for nuclear reactors, you need to concentrate this down, which is why you often hear the talk of centrifuges, because you can separate these guys by mass, because 235 weighs a little bit less than our 238, which is our most common form. However, by bombarding 238 with neutrons, we can convert it into plutonium, another type of radioactive material that can be used in reactors. So that's going to go, you bombard it with a neutron to form 239, which after a half-life of 2.3 minutes forms neptunium and a beta particle. Give it another 2.3 days, and it'll form plutonium and another beta particle. So it's shifting 2 elements to the right as it does so. So here's a generalized reactor, and we'll look at that more, what all this involves in a bit. But you can see here that we have the rods, the fuel rods, fuel elements in black, these control rods that are pushed in and pulled out. We have a thermal shield right here. We have some sort of coolant in. And you have this concrete biological shield there. So we'll talk about all those in a little bit. So let's still talk about the first nuclear reactor, which is kind of interesting. So after the nuclear fission was first discovered, the first working reactor that had a continuous stream of essentially, where Enrico Fermi created the first working reactor. It didn't really absorb the energy, but he was able to get a consistent formation of neutrons, so he could keep the reaction going to prove that in proof of concept, oh, we could use this for for energy source. And he did this 325 December 2nd, 1942 in a squash court. So he took a squash court underneath the stadium of University of Chicago and converted that into a lab, and they did that in there. And it's really kind of crazy because had things gone horribly wrong, Chicago would have been Chicago probably wouldn't be the same Chicago we know today. They made a pile of uranium and graphite blocks 24 by 24 by 19 feet. This was literally as you see in the bottom right corner, an atomic pile. And that's where we actually get the term. This is a pile of atomic bricks. And essentially they had a way where they can push the graphite bricks in and out to try to control this and hopefully halt it at the very beginning. But so, you have the little patent up there that it wasn't very fancy, but it was able to show that, oh, not only do we get it started and the neutrons build up and it had a consistent production, and then he shut it off. Just enough to make sure, yes, this will actually work. This can produce neutrons on a regular basis, and we can keep this as a constant reaction flowing. So, but okay, what is parts of a reactor? Reactor has, let's see, 5 basic parts. You have the fuel. This could be in many different types. You could be a metallic uranium. You could, most of the time, is maybe a ceramic uranium oxide or uranium carbide, put as a plate, pellet, pins, and they put in a geometric pattern so that we can keep all the neutrons in one place. Now, the fuel is often cladded with a stainless steel or zirconium alloy to kind of keep this from reacting with other and coming into contact with other pieces of the uranium. The neutrons can penetrate just fine. And in fact, the reactants change drastically over time, as you can see the top right picture. This is how it originally started out as, and after it reacts for a while, you can see how the density of the uranium changed from this kind of very porous block to this very chunky block in the picture below. Now, here's what's kind of not realized, is that you actually need a moderator to slow down the neutrons. Most reactors will actually want slower neutrons rather than faster neutrons as they're getting shot out of there. It's easier to absorb the slow neutrons than it is to absorb the fast ones. So they need things like water. They need light elements like hydrogen in the water, or sometimes graphite or beryllium. That's actually going to essentially, as the neutrons get flung out, they're going to bounce off there and lose some of their energy. They're going to be slowed down as they get absorbed into the uranium. Now, there are some reactors that can work with fast neutrons, but not all of them do. Now, the control system are going to be powerful neutron absorbers, like boron or cadmium, that are just going to suck up the neutrons, and that's going to be how we stop the reaction. So those are going to be how we control the reaction. Those are going to be pushed partially in or partially out to keep the reaction at a constant rate. If we want the reaction to go more, we'll pull them out a little bit. If we want to slow it down, we'll push the control rods in a bit, and they're essentially going to control how many neutrons, what percentage of the neutrons get absorbed. And we can essentially slow the reaction down. And then the big thing is a heat removal, which is also going to be how we're going to generate our power. Most of the energy from these things are going to be the kinetic energy from the fission products. It's going to be converted into a heat. And we need some way to transfer that heat away. Sometimes it could be air. Sometimes we can use helium gas or CO2. Oftentimes you see it as water, but it could also be organic compounds or even liquid salts like sodium and lithium. That is just going to absorb that heat and transfer it somewhere else. Now, whether this is the water is directly used for this, or it's linked, as we'll see in the next picture, to another set of water. We're going to boil some of this water, and it's going to then, the steam is going to push a turbine, and that's going to be how we actually get the energy out. It's the same basic premises used in a coal furnace. You use the coal to heat the water, to turn into steam, to turn a turbine, which then is condensed, and then you do it again. But one of the most important parts there, that I often forgot, is the radiation shield. We need both a steel lining to prevent thermal damage to the reactor, so it's not going to melt on us. You also need a concrete, the biological shielding, to prevent all the scientists running that, or all the engineers running that, from dying. So that's another important part of every reactor. We have some sort of shield here. It's going to prevent any loose radiation from escaping and damaging people around us. So timer's actually up, but I'm going to keep going for another minute. So this is just a couple images of some various types. This is not all of them. This is just a few examples. So see, here's a scheme of how a generator works. This one is a pressurized water reaction. So you have the fuel rod core right there. You have a pump of coolant water that's going to cool the rods down. And that is in a separate circuit from the steam generator line. So this is going to be pump water in. The heat is going to flow from the primary loop into the steam loop, boiling the steam, which is going to turn the turbine and generate the power. And then we're going to have a condensing cooling water that's going to absorb all the heat from the steam and then cool down. And this condensing line is actually going to go to those, those nuclear towers we always see. Those are all cooling towers that essentially use the nature to cool the water back down, so we don't have to spend a bunch of energy cooling it down. Now, the boiling water reactor, the steam line and the coolant line are in the same loop. So it doesn't have to be separated like this. And then, of course, here's an example of a liquid metal-cooled reactor. So the coolant is liquid sodium. So you have a sodium loop right here. And actually, you have another sodium loop absorbing the heat, and then the steam line. Once you get through the whole issues with sodium, sodium is actually very good at efficient heat transfer medium. So there's some, as I said, there's some complications, but it's good at transferring heat, so we can keep most of the heat transferred pretty well. Okay, so I'm going to go ahead and let's see. Well, I'm going to wait till my time warns me I'm almost out of time, and then I'll jump to the next meeting. So nuclear waste. This is kind of one of the two large problems with nuclear reactors. As most of you should have been alive when Fukushima happened, so essentially, when reactors do fail, it's usually, when we hear about it, it's usually pretty bad. But most of the time, there's very minimal danger. But when it goes bad, it goes really bad. Like Fukushima, they had an earthquake, they had the emergency shut off, and that was all well and good. They lost power, but they had the backup generators that were working. And then when they had the tsunami that followed the earthquake, it flooded the generator room, shut off the backup generators, and that's where you had the problem. It's all well and good to plan for one disaster, but two disasters, it's a little bit harder to plan for. And so that was kind of the problem there. But nuclear waste is the other really big problem. That everything is a first order decay. And so that means they have a constant half-life, and we cannot change this half-life of the natural decay process. Now, once you have a spent fuel rod, radioactive products need to undergo 10 half-lives before it's considered no longer a danger. So, problem with that is if the half-life is 1,000,000 years, you're holding on for this for essentially 10 million years. So we have to really plan this through. Now, there are certain ways to reprocess this ore, extract out certain long-lived reactions to maybe reuse some of these radioactive materials in other types of reactors, and thus convert them into less radioactive products and still get some more energy out of it. So it's not the end of the world, but it's one of those fields where we need to really think ahead. We need to start using new science to make this safer. Because, I mean, strontium-90 only needs 200 to be stored for 288 years to essentially be safe. Plutonium-239 would have to be stored for 240,000 years. So you either want to use up the plutonium or at least separate it so it can be disposed in a separate container, because the reaction waste only has to be stored as long as the longest lived thing. So if you have only strontium in there, you don't have to worry about it nearly as much. Okay. We'll come right back to the meeting and talk about how does a nuclear bomb differ from a nuclear reactor. See you in a minute. Right. So, what separates a nuclear bomb from essentially a nuclear reactor is the idea of a runaway chain reaction. The idea is that a nuclear reactor is held at a critical mass where we have just the right amount of neutrons being absorbed to neutrons being produced to keep this at a steady state reaction. Essentially, it's going at a constant rate. Now, if we were to absorb one neutron and produce two, and then both get absorbed and two produce four, and then four produce eight, so it would have essentially a runaway reaction. And each of these things would generate more and more heat, which will generate more and more pressure, and that's where essentially generates the explosion. So what happens in a nuclear bomb is we have what's called a supercritical mass, where we have just a certain ratio of uranium put together that a certain density of uranium together that enough neutrons get absorbed per produced that it chains and gets more and more and more, producing more and more energy, building up all the pressure that we need for that explosion. Now, how do you keep that from accidentally going off. And that's where you actually have, in a bomb like this, you store uranium in two subcritical mass segments. You see in here in the diagram of the bomb that S is the U-235 projectile ring, so that's one subcritical mass, and in H we have the U-235 target rings. And so when this hits the trigger, right down there, A, essentially it's going to launch the, you say you're going to essentially launch this ring into there, and launch H into S. And then from there, it's going to react, at which point we form the first, or there's going to be something in there that's going to shoot. So G is the polonium beryllium initiators. That's essentially going to shoot that neutron into there and start that chain reaction. So once together, we have that big bomb, boom. The first two nukes we shot were the Fat Man and the Little Boy. Now, the Little Boy right here is the standard one, which just has a uranium explosion. But try to remember, but the Fat Man actually was a hydrogen bomb, and they use a uranium explosion, and they have a way to contain that energy such that you start generating fusion of hydrogen atoms, like create essentially a miniature star, which essentially once you get the heat and pressure needed for fusion, it produces a whole heck of a lot more energy. So that bigger explosion in of itself. So speaking of that, we'll go into one other aspect of nuclear chemistry, which is fusion. So all elements are essentially produced by the fusion of hydrogen and helium. That's how everything in the universe was created. Essentially, in the stars, you have tremendous pressures and tremendous energies. And you start clumping together two hydrogen atoms, produce a positron and a deuterium. And then a deuterium gets fused together with a hydrogen and produces a helium with a 3 mass instead of a 4 mass. Then helium of 3 mass comes together to form a normal helium atom and two hydrogens, and this keeps going. This keeps going until we essentially run out of all hydrogen. So most stars are hydrogen, helium, and undergo these basic fusion reactions. Now, the first reaction here produces, look at that, negative 8.985 times 10 to the 10th joules per mole alone. But of course, as I said, it needs incredibly high temperatures over, what's that, like 40 million degrees Kelvin, and incredibly high pressures. But the surface gravity of the sun alone is 274 meters per second squared. So that's the gravity just at the surface compared to our measly 10 meters per second squared. And gravity increases as we get closer and closer to that center. I'm not sure if we actually measured the gravity at the center of the sun, but so that explains how we go from hydrogen to helium. But what about everything beyond that? Well, once all the hydrogen gets used up, the helium will start to react. Helium needs more energy and more pressure, and so the star will actually change once it's consumed all the hydrogen, and will start to go through a different reaction. So two helium atoms can form a beryllium, and then this beryllium atom can then react to form carbon. This carbon atom can react to form oxygen. And we have a series of rapid fusion reactions that produce every element up to iron, 56. These will act for a series of slow and rapid neutron capture reactions that will form many of the heavier elements. Now, okay, I'm not going to say I know everything about this because it's all some really, really, really heavy physics stuff. But essentially, once we start forming iron, the star will start to really kind of decay. It will generate a whole bunch of these trace elements and eventually start to collapse in on itself and go supernova. When a star explodes, it's going to have some ratio of all this carbon, beryllium, iron, and everything in there. When it explodes, it flings that out into the galaxy. All that stuff can then coalesce into a planet, which is kind of what we did. Earth was a big dust cloud in the solar system that when the planets were coalescing, we had our gas giants like Jupiter and Saturn and the Sun. We are kind of what didn't coalesce into them, coalesced into Earth. So all the elements that are in Earth were originally formed by these solar fusion reactions. So kind of like every time a star explodes, you're seeding the life you need for a future planet, all the material for a future planet. But it takes a long, long time to coalesce into that planet. So, but how could you calculate the energy of the nuclear reactions? What is the energy of all these reactions? So that if you've looked at the math, the first law of thermodynamics says energy is neither created nor destroyed. So if matter is conserved, how do nuclear reactions generate energy? We're not actually breaking any bonds, so where's the energy coming from? If you add up the mass of all the products and all the reactants, it looks like all the mass is conserved. So where's this energy coming from? Well, we all hopefully know E equals mc squared. That energy is mass times the speed of light squared. How do we calculate the energy produced? Well, when we actually add up the mass on both sides, we see we lose a tiny bit of mass as energy. Remember, I briefly mentioned this, but when you look at protons and neutrons together, there's a little bit of energy called the weak nuclear force, which is essentially what's holding the protons and neutrons together. If you add up the sum of this product, the actual atomic mass of this product, and the actual atomic mass of that reactant, and the actual mass of a neutron, you'll see the masses do not perfectly add up. The left side mass and the right side mass are not quite the same because the energy lost, the mass lost is as that nuclear energy. So we actually have a small change in mass as it undergoes this decaying reaction. Now we call this change in mass as the mass defect. And we can physically calculate this. But to do this, you need an exact mass. You cannot use an isotopic mixture. We cannot use the number that is in the periodic table. You would have to actually use the exact mass of that very one isotope. So we're just looking at one type of atom being lost, not carbon 12, carbon 13, and carbon 14. We're looking at just carbon 12, or carbon 13, or carbon 14. One, not all three. We're not looking at chlorine 35 and 37, whatever. We're looking at just one of those isotopes. So how would you do that? So if I did uranium-238 undergoing alpha decay to thorium-234, the exact mass of uranium is 238.0003, which is AMU per atom, or you could use that as grams per mole. Thorium is 233.9942. This is one of those things if you did this, you could not round. You do not want to round because you don't want to lose the small amounts. And alpha particle is 4.0015. So you'd add thorium to alpha and subtract that from the uranium. So products minus reactants, really. And see, if you add those up, I'm not going to make you do this right now, but if you add those up, the mass difference is 0.0046 grams per mole. Now, in order to get the units right, joules can be used as units of kilograms meters squared per second squared. Well, the meters squared per second squared come from the speed of light, which is meters per second. But so that means our grams per mole, we need to convert that into kilograms per mole. So we're going to divide that by 1,000 grams to get in kilograms. But you take that number times the speed of light, and that would calculate how many joules of energy gets released when uranium undergoes alpha decay to thorium. This is just a natural alpha decay product. This is just alpha decay product. This isn't even nuclear reaction. This is not a nuclear reaction. This is just, this goes on its own. How much energy that is. So if you're holding onto a block of uranium and 1 mole of uranium were to undergo and decay, how much energy would you be absorbing? And that is quite a lot. So I'll just quick do this one. But uranium nuclear bonds work on 1 or 2 mechanisms. This guy, tellurium, zinc. How much energy is, I think I deleted the other mechanism because I didn't want to further confuse anyone. So essentially here, how much energy is produced through this first mechanism? So I'm looking at the products, 136.92532 plus 96.910950716 plus 2 times a neutron, which is 1.00866. So all the reactants add up to 235.8535907. All crap. Need to annotate. So all the products add up to 235.8535907. All the reactants, uranium and 1 neutron. One neutron is 236.0525831. So 535.907. So the mass defect, the difference between these two, is equal to, it's a small difference, but it's a significant difference. 9899232. We have to divide that by 1,000 and multiply by the speed of light squared. 0.998 times 10 to the 8th. And you'd get how much energy is produced per 1 mole of uranium. And you'd get like 1.78 times 10 to the 13th power. Now, here's what's different, a uranium bomb from a natural nuclear process. This guy, last slide, assumes 1 mole of uranium decays. Now, because of the slow half-life of uranium, you're not going to get 1 mole of uranium decaying all at the same time unless you had like a mountain of uranium. Then you would have small portion being a mole decaying and producing that energy, that deadly energy. Now, a nuclear reaction, you're inducing decay right away. You're not letting this decay on its own, you're initiating this. So if you have a mole of uranium, you're going to get that mole of uranium reacting. You're not going to say, oh, I'm going to have 1 small fraction of this uranium reacting. You're going to have all of this uranium reacting. And so you get a whole heck of a lot of energy produced all at one time, which is channeled into various gases and heat as you explode and the gases expand and they're hot enough to vaporize skin, bone, everything. So very, very dangerous. And one last idea here. I think this is maybe the last one before clicker question in the end. I'll have to check. I can't really remember. But so as I said, iron is the final fusion product that a lot of them get seen. Why is that? Because iron is the highest point of what's called nuclear binding energy. This mass defect is due to the strong nuclear force. That if you count the total number of the binding energy per nucleon, which is protons and neutrons, you can get a ratio of how much energy they get per proton they have in there, per nucleon they have in there. And you get like an average binding energy. Well, for iron, you max out. So up until you get to iron, the higher you get on this table, the more spontaneous it is. The easier it is to form that because you have a higher binding energy. Essentially, you're trying to find the peak point. Well, the reason we stop at iron was iron is the absolute peak. Everything is going to be fusion to get to here. Everything below that, you see, it starts to trail off. So copper and arsenic and molybdenum are still pretty high, but as you get lower and lower down, there's lower binding energy per nucleon. They get more nucleons, but not nearly as much binding energy per nucleon, so it's a smaller ratio. So every element to the right of iron will undergo fission, trying to get to iron or something close to iron. Every element below iron will try to fuse to get to iron. So the idea is like we're trying to reach the maximum binding energy, which is why iron is our stopping point. But there's getting some pretty heavy physics stuff that I'm not really super comfortable talking about. Okay. So last clicker question. Equation E equals mc squared can be used to determine the energy produced for what? Is it for all nuclear reactions? For only fission reactions? Fusion reactions? Only for naturally occurring radioactive decay processes.
Sure.
I think this is like maybe the last slide is where we're gonna finish up. As I said, I'll send this email out to remind you guys, this is the last test. So finish strong, work on this, finish up. I'm not really intending to do a final. A final is going to be too big of a pain in the ass. You guys are, what I might end up doing is I might end up either taking either your average test score or just your highest test score and doubling it or whatever for the final. So finish strong. I'll figure out what's best for all of you. We're not going to have to worry about a final in this class. Of course, though, if
your ass back in the shower, bitch.
if this test is as hard as I don't know Hunter's saying, maybe this is your final. But
Yes.
well, okay. Stop it at the 2-minute mark. It's gonna send me emails, email, blah blah blah. Okay, basically anything, everything. it can be used to do for all. It's like you can do it for fusion, you can do it for fission, you can figure out how much energy is absorbed when you fuse a star. You can use it for how much energy. You can use it for how much energy is created by a nuclear bomb. Do this for natural decay. That's all I have. That's really all I have for this class. Said I'm not going to include this in, not going to make you do any of this math. I think we're good here.
When is the test due? Still.
It's, I'd say Friday, but I can give you more time. I really don't care because, especially if this is your final thing. I mean, I'm going to give you till like Monday of finals week, because just so I have some time to grade it all, hunt down the last few people that need to finish things. Just keep on working on the homework. One thing I'll note, and I'll send this as an email as a reminder, is that next week I'm going to put in zeros for every person who hasn't turned in a certain lab, and those are open to change when you turn in the labs. But just so you know, if you don't turn in this lab, what your score will be. Because, as I said, it auto drops the 2 lowest scores. If I don't have any grade in there, it's not calculating for that. So that you have a last bit of chance to turn in this lab or that lab, and you know, like, oh, if I don't turn in acid-base lab number 9.
I'm only missing this lab.
Yeah, if you're missing this lab, they'll tell you exactly what score you're going to get. So if you're like, oh, I'm still getting an A, don't worry about it.
You said that it won't. You said that it won't drop it automatically if it's a 0.
It will drop it automatically if it's a 0. The only time it won't drop it if I don't put a score in there. So, like, for example, if you have 0 score for this lab, then it's not dropping it because it's just assuming there's no lab there. So, like, for example, if you haven't turned in anything for a lab, the only zeros I put in for labs is
I got to do these two.
the only 0 I have for labs are labs that came before we had quarantine. So I haven't put any zeros in for any of the other labs.
Okay, so I got to do
So
3.
next, starting like maybe Friday, I might start putting some of the zeros in so you can see. Hard, fast rule, if you're missing 3 or more labs, or you have a really shitty lab and you're missing 2 labs, you may want to turn in 1 more lab.
Yeah.
But most of the time, if you're only missing 2 labs, you're usually pretty fine. Pretty fine. I say that realizing though that a lot of people got burned by the equilibrium lab being way harder than they expected it to be.
No.
So if we have all good lab grades and we just decide maybe we don't want to do the last 2.
Yeah, I'm going to put in the score for you, and
Okay.
if it still says A, by all means, you're good. That's what I'm saying. If when I put in the score for you and it says and you still see A on the Schoology, I'll be like, and I might even send you a reminder like, oh, I put in the zeros and that knocked you down to a B. You might want to do 1 more lab. But if I put in the zeros and you're just like, oh, still got an A, I'm just going to leave it and you'll be fine, and we're not going to worry about it. So, as I said, yeah, I'm going to put those in so you know what you're going, and you have like finals week to finish up whatever needs to be finished up. And I'll try to send emails to remind you, like, oh, I still need this from you for in lab.
I do 3 labs.
What? Because yeah, Quintus, yeah, I gave you that the grade that you and Logan and whatnot and Madison were working on. I scored that one for everyone. But okay. So anyway.